Hello everyone, I'm Bhaskar Pataya, a second year PhD student advised by Professor Rajiv Singh at Karnal. Today I'll be talking about our work titled What Obstructed Skies Teach Us About Satellite Internet and present some of our interesting findings. This work was done in collaboration with Hamas Pentangit and Professor Rishabh Nikonam from University of Let's first look into how satellite internet ecosystem works. We'll be specifically looking at Starlink. End users can use Starlink terminal to get connected to the satellites in space, which is both connected to ground station, and finally the ground stations are connected to the internet. But here the data flow looks like it goes from end users to the Starlink terminal, then to the satellite, and then the ground station, which is finally connected to the internet. With this, end users can access the internet from nearly every location on Earth. And Starlink can provide internet connectivity in remote and isolated areas. And this could be particularly useful for monitoring remote power grids or detecting forest fires. However, the terminal requires a clear view of the sky. And in isolated areas, it could be obstructed by trees or buildings because of lack of maintenance. And in this work, we wanted to understand the impact on satellite internet under such obstructed conditions. And during this exploration, we uncovered some of our interesting findings regarding how Starlink responds to such obstructions, which we will explore today. In this talk, first I'll describe our experimental setup. Then we will look at how does the Starlink terminal behave without obstruction to establish a baseline. And then we'll look at the aerial with obstruction. And finally, we'll look at how Starlink copes with such obstruction. And then I will talk about the previously unknown phenomena which we call as responsive routing. To simulate obstructions in a controlled and a reproducible way, we used a metal sheet to block the dish's line of sight for to specific parts of the sky. And it covers obstructions caused due to trees or buildings. We kept our experimental setup on the rooftop of a building here at Karnal and chose a location with a clear sky view so that there are no unintended obstructions. But this, we used the two-dish setup where a control dish would serve as a reference baseline and a test dish that we used for conducting our experiment. So let's look at how does it look without the obstruction. To establish a baseline, we first kept both the dishes unobstructed and measured RTT and packet loss. On the left-hand side, we plot RTT for more than a week, and we can see that for both the dishes, RTT look very similar. And on the right-hand side, we show packet loss over the same period, and again the behavior is very similar. One thing to note here is despite the loss spikes nearly always happen past midnight before. And we think this could be because of our routine Starlink maintenance or some network handy events happening during off-peak hours. Now let's look at how does it look like with obstruction. So here with the obstruction, as you can see on the left-hand side, RTT is increased, and as you can see on the right-hand side, the loss is also increased. However, it only increases by a few percentage points. Moreover, because of the obstruction, we observe a change in the connection behavior. So here on the left graph, on the x-axis, we have the limit, which is the angular distance from north, and CDF on the y-axis. And in the graph, the dashed lines represent the obstructed as So here, as we can see, the solid lines uh, represent the unobstructed scenario, and the blue line for the control loop and the red line for the tangent, they are nearly overlap, which means they were connected to the satellites in the similar region. However, in the obstructed scenario represented by the dotted lines, we can see that both of them shift towards north. Even though the shift for the test dish is more than the control dish, but here we expected the shift for the test dish but the chip for the control dish was unexpected. We kept both the dishes 6 feet apart, as shown in the image on the right, and also made sure with the obstruction map provided by the Starlink application, which is used to detect the obstruction, and made sure that the obstruction for the test dish is not entering with the control dish. This change in connection region for the control dish could mean either the obstruction was still obstruction for the test dish was still affecting the control dish, or obstruction for one dish affects the connection region of the nearby dishes, which basically means that uh, connection change for one satellite would affect the connection change for other satellite. And this would be a security vulnerability on the Starlink side. And because of the obstruction and the change in the connection region, we suspected that both the dishes might be connecting to different satellites. Using the gRPC API, we isolate the trajectory of the connected satellite for both the dishes for and we then match the isolated trajectory with the publicly available satellite information about the Starlink satellites and find the closest mapping satellites to the with respect to the trajectory. And if the closest mapping satellite for both the test and the control dish are the same, then we classify them as connected to the same satellite. Otherwise, we classify them as connected to different satellites. And as a result, we found that with over a month of measurement, that in about 50% of the cases, the test dish connected to a different satellite as compared to the control. For comparison, when there is no obstruction, the two dishes connect to the same satellite more than 97%. The obstruction caused a change in the satellite connector for the test dish. Now let's look at how Starlink copes with such obstruction. Let's look at a fine grained view of how Starlink behaves under such obstruction. In this figure, we have tan on the x-axis, and on the y-axis, we have RTD shown by the colored band and loss shown by the dots. At t equals to 12 seconds, the disk performs a routine satellite change. Starlink typically switches satellites about every 15 seconds. So we see the handovers around 12, 27, 42, and 57 seconds. After the switch at t equals to 12 seconds, the obstructed dish started getting higher RTD and higher loss. And at about t equals to 16 seconds, the RTD reaches nearly 250 milliseconds and loss of nearly 100%. You'll note that because of the measurement methodology, loss of 5 means loss of 100%. And due to such high loss in RTD, the test dish switches to a different satellite. And after the RTD again goes back to normal to about 50 milliseconds and loss goes back to 0. And we can also see the responsive routing, which it changes the connection between the 15-second connection window and the trajectory maps as well. Here, as shown by trajectory 1, the dish first connects to one satellite and then and these trajectories we call as partial trajectory since it's much smaller and then it switches to another satellite which is branded by trajectory 2. So in the same 15-second window, the test dish switches the satellite as shown in the trajectory. And to further explain the extra partial trajectory, which we saw earlier in the previous chart, we explored multiple hypotheses that might explain or negate the responsive one. As shown here, we have the trajectory map of the current window and the next window. We can see an extra partial trajectory in the current window, which lines up with the trajectory in the next window. It could be that because of our measurement methodology, pixels from the next window would have underflowed into the previous window, which is marked on the current window. We call such extra partial trajectory as underflow. If they line up with the trajectory in the next window, and overflow if they line up with the trajectory in the previous one. We explored all such overflows and underflows scenarios and classified them with 3 thresholds. Here, a threshold of zero means that the trajectory, the partial trajectory overlaps with the trajectory uh, in the uh, adjacent windows, and the overlap is an exact overlap. Uh, Whereas with the threshold of one, the we have the a partial trajectory within a distance of one pixel, and with the threshold of two, that basically means the partial trajectory is within the distance of two pixels. And as we can see, the numbers doesn't change by the upper threshold of one. So here we can see that for underflow, for the test test, the underflow percentage is about 27.42%, and with the threshold of 1, and for the threshold of 2, it's about 27.7%. And it's similar for other numbers as well. Though, with the threshold of 1, we can say that in 21% of the cases, when the test date was connected to a different satellite, we observe an extra traffic, which basically means that in 21% of the cases, the test just switch satellites between the same connection window. Moreover, we also found that before switching, the test dish initially connects to the same satellite as the control dish. But here, as shown by the trajectory one in both test and control dish, they are at the same place. So that basically the test dish first connected to the connect to the satellite, first connect to one satellite and then move to a different satellite as shown by trajectory two. But trajectory one for the test dish overlaps with the trajectory one of the control dish. That basically means that they both connected to the satellite in the same region. And we can see that, uh, I note that here the trajectory 2 is an underflow. To evaluate this hypothesis that initially both the test and the control dish connect to the same satellite before the test satellite moves away because of the obstruction, we ran a similar analysis. And it we use a relaxed classification where we don't give overflow or underflow cases higher precedence in the same satellite case. Then, in over 67% of the instances, both the dishes initially connect to the same satellite, and uh, only later the test date is moved away. And even with the much stricter classification, where overflow and underflow cases takes precedence, we still see this pattern in about 25% of the cases. So even though Karun can detect obstructions and react to them, it doesn't seem to remember those obstructions when choosing the initial setup. So the dish first connects and then experiences the degree performance and then it is. So this is more of a reactive strategy. But if Starlink were to use a more proactive strategy, which avoids that which avoids satellites in the obstructed regions and then have information about the obstructed region as well, users could likely get a better performance and avoid unnecessary handling. To conclude, we found that obstructions generally degrade the performance. Even though they do not degrade performance a lot, they still degrade the performance. And this is because uh, the less performance or degradation is because Starlink adapts to such obstruction by switching to a satellite. However, Starlink does this reactively, where they first make the connection, see if of higher loss or latency, and then switch. But if they were to do it proactively, uh, and they can avoid connecting in the obstructed region, and the user should get a better performance. Thank you.